Welcome, dear friend. I've been quietly awaiting your arrival. Here, within the ancient stillness of Sleepy University, you may find true solace. I am Chancellor Eldrin, here to gently guide your way. Now, I activate my balm of stars, a soft light to comfort your rest and ease your learning. Come, let us softly explore the vast wisdom that waits, where quiet calm brings clear understanding. For many, the word Rome evokes images of emperors, gladiators, and vast armies. However, beneath the surface of military might and political intrigue lay a remarkably sophisticated understanding of engineering. It's easy to overlook the crucial role engineers played in the empire's success, but without their innovations, the legions couldn't have moved, cities couldn't have flourished, and the Roman way of life couldn't have spread. We study Roman engineers not simply to admire their achievements, but to understand how they solved problems that are still relevant today. Their ingenuity, their ability to use available materials and knowledge to overcome logistical and structural challenges, provides a powerful case study in applied problem solving. Consider the sheer scale of the Roman Empire. Maintaining control over such a vast territory required an incredible infrastructure of roads, bridges, aqueducts, and buildings. Each of these demanded careful planning, precise construction, and a deep understanding of materials science. We're not just talking about building structures, we're talking about creating systems that could withstand the test of time and the pressures of a massive population. Their solutions, surprisingly simple yet incredibly effective, shaped the world we live in today and continue to influence engineering practices even now. Consider the longevity of Roman structures. Many Roman roads are still in use today, nearly 2,000 years after they were built. Aqueducts continue to channel water, and buildings like the Pantheon stand as testaments to Roman engineering skills. This isn't just luck, it's a direct result of their innovative use of materials, especially concrete. However, Roman concrete isn't quite like the concrete we use today. Modern concrete relies heavily on Portland cement, a material invented in the 19th century. Roman concrete, on the other hand, was different. It incorporated volcanic ash known as pozzolana, which gave it unique properties. It wasn't just stronger, it was also self-healing. Microcracks would react with seawater, forming calcium carbonate that effectively sealed the cracks and prevented further damage. This self-healing ability is something modern engineers are actively trying to replicate. Additionally, producing Roman concrete required much less energy than making Portland cement, making it a potentially more sustainable building material. Understanding how they achieved this remarkable durability is important not only for appreciating history, but also for solving current construction challenges. Beyond the materials themselves, the Romans were masters of standardization and logistics. Their road network, for example, wasn't just about getting from point A to point B, it was a carefully planned system that facilitated trade, communication, and military movement. Roman roads weren't simply paved over existing terrain, they were meticulously engineered to be straight, level, and durable. They used a layered construction technique with different materials for various purposes, ensuring proper drainage and load distribution. This standardization meant that materials could be sourced locally and construction could be carried out efficiently across the vast empire. The same principle applied to other infrastructure projects. Aqueducts, bridges, and buildings were all designed with a degree of modularity, making them easier to build and maintain. This focus on efficiency and standardization wasn't just about practicality, it was a key part of Roman power. A well-maintained infrastructure allowed for rapid troop deployment, efficient transportation of goods, and effective communication throughout the empire. This course will explore these innovations, examining the techniques, materials, and principles that enabled Roman engineers to create a lasting legacy. Over the next 12 chapters, we'll embark on a journey through the world of Roman engineering. We will move beyond the grand monuments and explore the underlying principles that allowed the Romans to construct such remarkable structures. This isn't just a historical survey, it's an investigation into the techniques, materials, and problem-solving approaches that continue to influence engineering today. We'll begin by examining the materials they used: concrete, brick, stone, and wood, and how they were sourced, processed, and utilized. Then, we will delve into the specific types of infrastructure they built: roads, aqueducts, bridges, buildings, and harbors, analyzing the engineering challenges they faced and the innovative solutions they devised. We will also explore the organizational aspects of Roman construction, examining how they managed large-scale projects, secured resources, and maintained quality control. Each chapter will build upon the previous one, gradually revealing the full scope of Roman engineering expertise. Our focus will also include case studies, where we will examine specific structures such as the Pantheon, the Pont du Gard, and Hadrian's Wall to illustrate the principles we discuss. We'll dedicate significant time to understanding Roman concrete, examining its composition, properties, and advantages over modern concrete. We'll explore the role of pozzolana, the unique chemical reactions that contribute to its durability, and the potential for replicating this technology in the 21st century. We'll also investigate the Roman approach to hydraulics, exploring their understanding of water flow, their methods for building aqueducts and canals, and their solutions for managing water resources. Another key focus will be on Roman surveying and construction techniques. We'll examine their tools and instruments, their methods for laying out structures, and their techniques for ensuring accuracy and stability. Finally, we'll consider the broader context of Roman engineering, exploring its relationship to Roman society, politics, and military power. This isn't simply about technical expertise, it's about understanding how engineering shaped the Roman world and left a lasting legacy that continues to influence us today. Throughout this course, we will use a variety of resources: archaeological evidence, historical texts, and modern scientific analysis to reconstruct the Roman engineering landscape. We will examine the challenges faced by Roman engineers, the innovative solutions they devised, and the long-term impact of their work. We will also consider the ethical implications of Roman engineering, exploring how their decisions affected the environment, the workforce, and the wider community. Ultimately, this course aims to give you a comprehensive understanding of Roman engineering, not just as a historical phenomenon, but as a source of inspiration and insight for modern engineers and designers. So, prepare to explore the fascinating world of Roman technology and discover the secrets of a civilization that built an empire meant to last for millennia. Before we dive into the specifics of Roman engineering, it's crucial to understand the historical context in which it flourished. The Roman Republic, initially a small city-state in Italy, gradually expanded its influence through military conquest and political alliances. This expansion wasn't just about acquiring territory, it was about integrating diverse populations, managing vast resources, and maintaining control over a growing empire. This created an unprecedented demand for infrastructure, roads to connect distant provinces, aqueducts to supply cities with water, bridges to cross rivers and ravines, and fortifications to defend against invaders. The initial period of the Republic was marked by internal strife and political instability. However, the rise of figures like Julius Caesar and the subsequent establishment of the Roman Empire ushered in a period of relative peace and prosperity known as the Pax Romana. This era of stability allowed for unprecedented investment in public works and the development of a sophisticated administrative system. The Roman military played a crucial role in the empire's expansion and infrastructure development. Roman soldiers weren't just warriors, they were also engineers. They were skilled in building roads, bridges, fortifications, and siege engines. The construction of Roman roads, in particular, was a monumental task. These roads were not only for moving troops, but also for promoting trade, communication, and administrative control. The Romans used a standardized construction method with layers of different materials to create durable, long-lasting surfaces. This standardization allowed them to build roads quickly and efficiently over great distances. The Roman army also played a vital role in maintaining the infrastructure. Soldiers were responsible for repairing roads, bridges, and fortifications to ensure the empire's communication network stayed intact. The growth of Roman cities also created a demand for sophisticated infrastructure. Roman cities weren't just centers of political and military power, they were also hubs of commerce, culture, and innovation. Roman engineers designed and built a wide range of urban infrastructure, including aqueducts, sewers, public baths, amphitheaters, and basilicas. Roman aqueducts were especially impressive feats of engineering, transporting water from distant sources to cities and providing a reliable supply for drinking, sanitation, and irrigation. Roman sewers played a crucial role in maintaining public health by removing wastewater and waste, preventing the spread of disease. The construction of public baths, amphitheaters, and basilicas offered opportunities for recreation, entertainment, and religious worship. These structures were often decorated with elaborate mosaics and sculptures, reflecting Roman society's wealth and sophistication. The Roman focus on public works, combined with a strong administrative system and a powerful military, allowed the empire to flourish for centuries, leaving a lasting legacy that still influences us today. Let's explore the core of Roman concrete's durability: the pozzolanic reaction. Many people think of concrete as simply a mixture of cement, water, and aggregate, and that's true for modern Portland cement concrete. However, Roman concrete, while sharing similarities, operated on a different chemical principle. The main difference lies in the use of pozzolanic materials. A pozzolan isn't a binder by itself like cement. Instead, it's a reactive silica, or silica-rich material. Think of it as a catalyst or an ingredient that enables a reaction, rather than being the reaction itself. These materials, often volcanic ash as well as crushed brick or tile, contain reactive silica. When this silica contacts calcium hydroxide, also known as slaked lime, and water, a chemical reaction occurs. This process isn't instantaneous, it's slow and ongoing. The silica and lime combine to form calcium silicate hydrate, or CSH. This CSH acts as the binding agent in Roman concrete and is remarkably stable and durable, especially in marine environments. It is this CSH that gives the concrete its strength and resistance to weathering. Now, let's delve a bit deeper into the chemistry. Calcium hydroxide, also known as slaked lime, is created by adding water to quicklime or calcium oxide. This process, called slaking, releases a lot of heat. The calcium hydroxide then dissolves in water, releasing calcium ions and hydroxide ions. These ions are crucial for the pozzolanic reaction. The silica in the pozzolana reacts with the calcium hydroxide to form the CSH gel. It's important to understand that this isn't a single simple reaction. It's a complex process involving multiple stages and different types of CSH. The type of pozzolan used, the proportions of the ingredients, and environmental conditions all influence the characteristics of the resulting CSH. This CSH is what holds everything together, binding the aggregates into a solid mass. What's particularly interesting is that the CSH in Roman concrete tends to be less crystalline and more amorphous than in Portland cement concrete. This amorphous structure allows for greater flexibility and resistance to cracking, especially in situations where the concrete is subjected to stress or movement. The Romans, through centuries of experimentation, found the right balance of ingredients to create a material that could withstand the test of time and the harsh conditions of the marine environment. What makes Roman concrete truly remarkable is its durability in marine environments. Modern Portland cement concrete, while initially strong, tends to degrade over time when exposed to seawater. The seawater attacks the cement, causing it to crack and crumble. The alkalinity of seawater also plays a role in dissolving the cement matrix. Roman concrete, however, behaves very differently. The pozzolanic reaction actually enhances its resistance to seawater. The CSH gel formed through this reaction is less susceptible to attack by seawater. Furthermore, the reaction can continue over time, actually strengthening the concrete as it ages. Researchers have discovered that the Romans used a specific type of pozzolanic material, volcanic ash from the region of Pozzuoli near Naples, that contains certain minerals contributing to this enhanced durability. When exposed to seawater, these minerals form a rare mineral called tobermorite, which is incredibly stable and resistant to corrosion. This tobermorite further reinforces the concrete, creating a self-healing effect that helps repair cracks and prevent further deterioration. It's a fascinating example of how the Romans, through careful observation and experimentation, were able to create a material that defies the elements and continues to stand the test of time. Let's now discuss the essential building blocks, the lime and the aggregates. We've touched on lime, but it's worth a deeper dive. The Romans didn't use just one type of lime. They employed various formulations depending on resource availability and the intended application. Primarily, they used both quicklime and slaked lime, as we discussed earlier. Quicklime, calcium oxide, was produced by heating limestone, calcium carbonate, in kilns. This process, called calcination, drove off carbon dioxide, leaving behind the quicklime. The quality of the limestone significantly impacted the quality of the quicklime. Impurities in the limestone could weaken the resulting lime. They then carefully slaked the quicklime with water to create slaked lime, calcium hydroxide. The key was to control this process carefully. Too much water could lead to a weak, unusable lime. Too little, and the slaking would be incomplete. The Romans were skilled at judging the right consistency. They also understood the importance of aging the lime, allowing the slaked lime to sit for weeks or even months to let excess water evaporate and the lime to mature, improving its workability and strength. Now, let's move on to aggregates. Aggregates are the granular materials, typically stone, brick, or ceramic fragments, that provide the bulk and strength to concrete. The Romans were remarkably resourceful in their use of aggregates. They didn't rely on a single type of aggregate. They used whatever was readily available locally. In coastal areas, they often used volcanic tuff and pumice, which were lightweight and provided good insulation. In inland regions, they used limestone, basalt, and granite. They even reused fragments of broken pottery and brick, demonstrating a commitment to sustainability. The size and shape of the aggregates were also important. They typically used a mix of coarse and fine aggregates to create a dense, well-graded mixture. The coarse aggregates provided strength and stability, while the fine aggregates filled the voids between the coarse particles, creating a tighter, more impermeable concrete. They carefully sorted and graded the aggregates to ensure consistency in the mixture. The quality of the aggregates also mattered. They avoided using weathered or contaminated aggregates with organic matter, as these could weaken the concrete. The choice of aggregates significantly influenced the properties of the resulting concrete, impacting its strength, durability, and workability. The way the lime and aggregates were combined was also crucial. The Romans didn't just mix them randomly. They understood the importance of achieving a uniform mixture where the lime and aggregates were evenly distributed. They usually used a combination of manual work and mechanical mixing. Workers would layer the ingredients in pits and then tread them with their feet, or use wooden mallets to break up clumps and ensure a thorough blend. They also employed simple machines like levers and pulleys to lift and mix the materials more efficiently. The ratio of lime to aggregates varied depending on the intended use. For foundations and harbour structures, they often used a higher proportion of aggregates to make a stronger, more durable concrete. For walls and floors, they used more lime to create a more workable and visually appealing material. They also added other ingredients like pozzolanic and fibrous materials to improve the concrete's properties. Carefully selecting and combining ingredients, along with proper mixing techniques, was essential to the success of Roman concrete. It demonstrated their skill and ingenuity, that they could create a material that has lasted for centuries. Let's now discuss the actual process of mixing and the critical aspect of proportions. Roman concrete wasn't simply thrown together. There was a deliberate methodology refined over centuries. The primary method involved using large pits, often excavated directly on the construction site. Layers of aggregate were laid down first, followed by layers of lime, and then a controlled amount of water. This layering process was crucial for ensuring an even distribution of materials. The mixture was then trodden. Literally, workers would walk and tread on the materials to thoroughly combine them. This wasn't just brute force, it was a skilled process. Experienced workers knew the right amount of pressure to apply and the correct duration of treading to achieve a homogeneous mixture. They were looking for a consistency similar to a thick paste. The amount of water was critical. Too much water would weaken the concrete, while too little would make it difficult to work with. They relied on experience and visual cues to judge the right amount. The proportions of the ingredients varied depending on the application, but certain general guidelines prevailed. For massive structures like piers and foundations, a common ratio was approximately 1 part lime to 3 or 4 parts aggregate. This resulted in a very dense, strong concrete that could withstand heavy loads. For walls and floors, a ratio of 1 to 12 or 1 to 1.5 was sometimes used, creating a more workable material that was easier to mold and shape. The addition of pozzolanic material was also carefully controlled. Typically, pozzolanic material made up around 10 to 30% of the total volume. This provided the necessary reactivity to produce the durable CSH gel, boosting the concrete's resistance to seawater and weathering. It's important to remember that these weren't precise, scientifically measured ratios as we understand them today. The Romans relied on experience, visual judgment, and a deep understanding of the materials they worked with. They knew what a good mixture looked and felt like, and they adjusted the proportions accordingly. This reliance on practical knowledge and craftsmanship was a defining characteristic of Roman construction. Beyond the basic ratios, the method of mixing itself played a crucial role. Proper mixing ensured that the lime and aggregates were thoroughly combined, creating a homogeneous mixture that was free of voids or pockets of air. These voids could weaken the concrete and make it more susceptible to cracking. The treading process not only combined the ingredients, but also compacted the mixture, removing air pockets and increasing its density. The Romans also understood the importance of preventing segregation, the separation of ingredients during mixing. They avoided overmixing, which could cause the finer particles to separate from the coarser ones. They also used appropriate mixing techniques to ensure the ingredients remained evenly distributed throughout the mixture. This meticulous attention to detail, combined with their deep understanding of the materials they worked with, allowed the Romans to create a concrete that has endured for centuries, a testament to their skill and ingenuity. It's a far cry from our modern automated processes, but it demonstrates that a deep understanding of materials and careful craftsmanship can achieve remarkable results. Now, let's turn our attention to the fascinating world of Roman aqueducts. But before we delve into their impressive construction, it's essential to understand the fundamental principles they relied upon. Principles of hydraulic engineering. At its core, hydraulics is the study of fluids, liquids and gases in motion. The Romans, though they didn't call it that, were remarkably skilled at harnessing these principles. The foundation of their success was understanding gravity. Water naturally flows downhill. This seems obvious, but controlling that flow, maintaining consistent pressure and volume over long distances, was a significant engineering challenge. They understood that water seeks the lowest point and cleverly exploited this tendency. The concept of potential energy, the energy an object has due to its position, is key. The higher the water source, the greater its potential energy, and thus the higher the pressure to flow. This pressure is then converted into kinetic energy, the energy of motion, as the water moves through the aqueduct. Think of it as a controlled descent, carefully managed to deliver water to its destination. They also understood the concept of flow rate. This isn't just about how fast water moves, but the volume passing a point in a given time. It's directly related to the size of the channel. The wider and deeper the channel, the greater the flow rate. But there's a delicate balance. Wider channels increase friction, slowing the flow of water. They had to find the optimal dimensions to minimize friction while maximizing flow. Friction, as we touched on, was a constant concern. The roughness of the aqueduct's interior surfaces created resistance to the water's flow, reducing its speed and pressure. The Romans minimized this by using materials like opus sanguinum, a type of concrete made with crushed terracotta tiles. This created a relatively smooth surface, reducing friction and allowing water to flow more freely. Beyond materials, the gradient, the slope of the aqueduct, was critical. They needed a gentle slope, enough to allow water to flow but not so steep that it caused erosion or increased friction. This required meticulous surveying and precise construction. They used tools like the chorobates, a leveling instrument, and the groma, a surveying instrument, to ensure the aqueduct maintained a consistent gradient over long distances. It's important to understand they weren't simply building downhill tunnels. They were carefully calculating the optimal gradient to balance flow rate, friction, and pressure. Furthermore, they understood the principle of water hammer, the surge in pressure that occurs when a fluid in motion is forced to stop or change direction. They avoided abrupt changes in the aqueduct's path to minimize this effect. They also incorporated settling basins along the route to remove sediment and debris, preventing clogs and maintaining water quality. Finally, distribution was essential. Once the water reached the city, it needed to be delivered to fountains, public baths, and private homes. This was accomplished through a network of lead pipes and distribution tanks. The Romans understood the importance of water pressure in this system. Elevated tanks ensured sufficient pressure for supplying water to the upper floors of buildings. They also used strategically placed valves and regulators to control the flow of water to different areas of the city. It wasn't just about bringing water into the city, but ensuring that everyone had access to it. The entire system, from the source to the distribution network, was a marvel of engineering, demonstrating a deep understanding of hydraulic principles and a commitment to providing clean water to their citizens. They combined empirical observations with practical knowledge, creating a system that lasted for centuries. Now, let's proceed to the actual construction of these remarkable aqueducts. Most Roman aqueducts were not entirely underground tunnels. Instead, they followed routes that combined covered channels, tunnels, and, most impressively, arched bridges. The arched bridge was a revolutionary architectural innovation, allowing aqueducts to span valleys while maintaining a consistent gradient. The arch distributes weight outward and downward, enabling a much wider span than a simple lintel. This was essential for avoiding deep excavations and preserving the gradient. Construction began with a solid foundation, often a layer of compacted earth and stone. Then, they built wooden scaffolding known as centenae to support the arch during construction. The keystones, the central stones of the arch, were carefully placed last, locking the entire structure in place. The Romans were masters of concrete, opus cementitium, and used it extensively in aqueduct construction. This wasn't the same concrete we use today. It was a mixture of lime, volcanic ash, pozzolana, and aggregate, typically rubble or broken bricks. This mixture created a remarkably strong and durable material, capable of withstanding the constant pressure of water and the forces of nature. The Romans didn't pour concrete all at once. They used techniques called opus incertum and opus reticulatum to build up the walls with layers of rubble and mortar. Opus incertum used irregularly shaped stones, while opus reticulatum used pyramidal-shaped stones arranged in a diamond pattern. These techniques created a strong and flexible structure, capable of withstanding seismic activity. Once the concrete walls were in place, they would line the channels with waterproof materials such as opus sanguinum, the terracotta tile concrete we discussed earlier, to prevent leaks. Building tunnels involved different challenges. They often used fire setting, heating the rock face and then cooling it quickly with water, causing it to crack and fracture. They also used tools like picks, shovels, and drills to excavate the rock. Ventilation was a major concern in tunnel construction, so they used shafts and air ducts to provide fresh air for workers. The alignment of the tunnel was critical. They used surveying instruments and techniques to make sure the tunnel maintained a steady gradient and direction. The most challenging part of aqueduct construction was often logistics. Transporting materials, quarrying stone, and coordinating workers required a lot of organization and manpower. The Romans had an advanced road network that made transporting materials easier. They also used a large workforce of skilled laborers, including stonemasons, concrete workers, and surveyors. Building an aqueduct was a massive project that often took years to finish. It needed a big investment of resources and manpower, but the benefits were huge. Aqueducts gave cities a steady supply of clean water, which improved public health and sanitation. They also helped the economy by providing water for farming and industry. The size and durability of Roman aqueducts show the brilliance and engineering skill of the Romans. Let's now focus on a specific example, the Aqua Claudia, one of the most impressive and well-preserved Roman aqueducts. Construction began under Emperor Caligula in 38 AD and was completed by Emperor Claudius in 52 AD. The Aqua Claudia was a monumental project, stretching for a remarkable 69 kilometers, 43 miles, from its source in the hills near Subiaco to Rome. It was designed to deliver approximately 320 million liters, 85 million gallons of water per day to the city. Unlike some other aqueducts that relied heavily on underground tunnels, the Aqua Claudia featured a significant section of elevated arches, making it a truly spectacular sight. For nearly 9 kilometers, 5.6 miles, the aqueduct was supported by arches reaching a maximum height of over 30 meters, 98 feet, in some locations. This elevated section allowed the water to flow by gravity, maintaining consistent pressure as it approached the city. The Aqua Claudia construction faced many challenges. The terrain was rugged and mountainous, requiring careful planning and execution. The engineers had to navigate steep hills, deep valleys, and unstable ground. They used various construction techniques, including tunneling, arch building, and concrete work. The arches were constructed with wooden scaffolding and carefully placed stone blocks. The concrete was mixed on site and poured into molds to form the walls and foundations. The aqueduct also included several settling tanks and distribution reservoirs to ensure water quality and availability. These reservoirs allowed sediments to settle out, preventing clogs in the pipes and fountains. The Aqua Claudia was not just a functional infrastructure project, but also a symbol of Roman power and engineering skill. Its impressive arches and grand scale aimed to impress and inspire the citizens of Rome. Today, the remnants of the Aqua Claudia can still be seen across the Roman countryside, serving as a testament to the lasting legacy of Roman engineering. The surviving arches and sections of the channel offer a fascinating glimpse into the past. The Aqua Claudia provided Rome with centuries of reliable, clean water, contributing significantly to the city's growth and prosperity. It stands as a remarkable achievement of Roman engineering and a symbol of the empire's strength and ingenuity. Studying the Aqua Claudia offers valuable insights into the construction techniques, materials, and engineering principles used by the Romans. It also highlights the importance of water management and infrastructure development in supporting urban populations. Now let's explore the impressive construction of Roman roads. These weren't just simple paths, they were advanced engineering projects designed to last for centuries, and many still exist today. The foundation of a Roman road wasn't a single layer, but a carefully built series of layers, each with a specific purpose. The very bottom layer, called the statumen, was the base course made of large, sturdy stones. Think of it as the skeleton that provides initial support. This layer wasn't meant to create a perfectly smooth surface. It was about drainage and load-bearing capacity. The Romans knew water was the enemy of roads, so ensuring proper drainage was crucial. They dug trenches alongside the road to divert water away, and the statumen layer, with its large stones, allowed water to seep through rather than pool on the surface. The quality of the statumen depended heavily on the availability of local materials. They used whatever large, durable stones they could find nearby. Over time, they improved the materials and techniques, which is an important point to remember. Above the statumen came the rudus, a layer of concrete composed of crushed stone, gravel and lime. This wasn't the smooth, refined concrete we think of today. It was a much coarser mix, almost like a rough aggregate. The Romans were masters of concrete and understood the importance of proper binding agents. Lime acted as the cement holding the crushed stone and gravel together. This layer provided a more level and stable surface for the final paving stones. Interestingly, the composition of the rudus could vary depending on the intended use of the road. Roads meant for heavy traffic, like those connecting major cities, would have a thicker and more robust rudus layer. Roads in rural areas might have a thinner, less substantial layer. The Romans weren't simply building roads, they were building infrastructure tailored to specific needs. Furthermore, they were incredibly resourceful. They often used locally sourced materials for the rudus, reducing transportation costs and maximizing efficiency. This practicality was a hallmark of Roman engineering. Finally, at the very top was the pavimentum, the actual paving stones. These weren't simply thrown down. They were carefully fitted together, often interlocking to create a smooth, durable surface. The Romans used various types of stone for the pavimentum, depending on availability and the importance of the road. Some roads were paved with basalt, a very hard and durable volcanic rock. Others used limestone or sandstone. The key was to select a stone that could withstand the wear and tear of constant traffic. The pavimentum wasn't always perfectly flat. Often, the stones were slightly raised, creating a camber or crown to allow water to run off. This was another example of the Romans' attention to detail and their understanding of practical engineering principles. The quality of the pavimentum was a status symbol. Major roads connecting important cities were paved with high-quality stone and meticulously maintained. Rural roads might have a simpler, less refined paving surface. It's important to remember that these roads weren't just about transportation, they were also about power and prestige. Building roads across the Roman Empire wasn't easy. The terrain was highly varied, ranging from flat plains to steep mountains, marshes, and even deserts. Each type of terrain presented its own engineering challenges. One of the biggest hurdles was dealing with mountainous areas. Simply laying a road through a mountain was not practical. The Romans had to find ways to overcome these obstacles. They used a variety of techniques, including cutting through mountains, building tunnels, and constructing bridges. Cutting through mountains was a huge task, requiring lots of manpower and engineering skill. They used tools like picks, shovels, and chisels to slowly and carefully carve a path through the rock. Building tunnels was even harder, needing careful planning and excavation. They had to make sure the tunnels were stable and wouldn't collapse. And of course, bridges were crucial for crossing rivers and valleys. Roman bridges were famous for their strength and longevity, often built to last for centuries. Roman bridges were not just simple straight spans across rivers. They often used arches. An arch is an extremely strong structural shape, capable of supporting a lot of weight. While the Romans were not the first to use arches, they mastered the technique. They knew how to distribute weight evenly across the arch, making it very stable. Roman bridges were usually built with concrete and stone. The concrete created a strong base, and the stone provided a durable, attractive surface. The Romans also employed a technique called opus caementicium, which involved layering concrete and stone to build a robust and flexible structure. This method allowed them to construct bridges that could endure natural forces like floods and earthquakes. The secret to a successful Roman bridge was careful planning and precise work. Every stone had to be placed carefully, and the entire structure had to be balanced perfectly. Marshlands and swamps posed additional challenges. Building a road across soft, unstable ground required a different strategy. The Romans often used wooden pilings to support the roadbed. These pilings were driven deep into the ground, providing a stable foundation. They then built a platform on top of the pilings, creating a raised roadbed. This design allowed the road to stay above water levels, preventing it from becoming submerged. Another method involved layering gravel and stone to form a compacted roadbed, helping to evenly distribute the road's weight and prevent sinking into the mud. The Romans were also skilled at drainage. They built ditches and canals to redirect water away from the road, avoiding waterlogging. It's important to remember that these weren't quick fixes. Constructing roads across difficult terrain demanded a significant investment of time, labor, and resources. Yet the Romans recognized the critical need to connect their empire, and they were willing to overcome any obstacle to achieve this goal. The Roman road network wasn't just a collection of individual roads. It was a highly organized and interconnected system. At its core was Rome, with a series of major roads called viae principales radiating outward. These roads linked Rome to all the major cities and provinces of the empire. Connecting to the viae principales was a network of secondary roads known as viae secundariae. These roads connected smaller towns and villages to the main road network. The entire system was carefully planned and maintained, ensuring that goods, people, and information could travel swiftly and efficiently across the empire. The roads weren't just about convenience, they were about control. They enabled the Roman army to move quickly and effectively, helping to suppress rebellions and maintain order. They also allowed the Roman government to collect taxes and administer justice. The roads stood as a symbol of Roman power and authority. The military impact of the Roman road network was enormous. Before the roads, moving an army was slow and a logistical nightmare. Supplying troops with food, water, and equipment was a constant challenge. The roads changed everything. Now a legion could march much farther in a shorter amount of time. Supplies could be transported quickly and efficiently, and communication could be maintained even across long distances. This gave the Roman army a significant advantage over its enemies, allowing them to respond rapidly to threats, suppress rebellions, and conquer new territories. The roads were often built strategically, connecting military forts and camps, which enabled the army to maintain a strong presence throughout the empire. They were also used to transport troops and equipment to the front lines, allowing the Roman army to launch offensives and defend against attacks. Beyond the military, the roads also played a crucial role in the economic and social life of the Roman Empire. They facilitated trade by allowing goods to be transported from one province to another, leading to increased economic activity and prosperity. The roads further enabled communication, allowing people to exchange ideas and information, which promoted cultural exchange and understanding. They were used by merchants, travelers, and pilgrims, connecting cities and towns and creating a network of interconnected communities. The roads also transported goods to and from ports, supporting maritime trade. The Roman road network was an impressive achievement of engineering and organization, showcasing the power and ingenuity of the Roman Empire. It was essential to the empire's success, and its legacy can still be seen today. let's understand the fundamental principles behind Roman bridge construction. And at its core lies the arch. The arch isn't just a curved shape, it's a brilliant solution to a problem. Traditional post and lintel construction, where you simply place a horizontal beam across two supports, has limitations. It restricts the span you can cover and requires substantial support. The arch, however, redirects the weight downward and outward along the curve into the supporting piers. The key to this is compression, the force squeezing the stones together. This allows for much wider spans and more efficient use of materials. The crucial element holding the arch together is the keystone, the topmost stone. Once the keystone is placed, the entire structure becomes self-supporting, with each stone locking into place. It's a beautiful application of physics, transferring the load from vertical to lateral forces and down into the foundations. Think of it like a hug. The pressure is distributed across the entire surface, making it incredibly strong. Without that keystone, the whole arch collapses. Now, the arch isn't limited to a simple curve. By extending the arch into 3 dimensions, we get a vault. Think of a barrel vault. It's essentially an arch extended lengthwise, creating a tunnel-like space. Roman engineers were experts in vault construction. They used different types of vaults, barrel vaults, groin vaults, formed by the intersection of 2 barrel vaults, and even more complex designs. Each vault type offered different structural benefits and allowed for the creation of larger, more elaborate spaces. These vaults weren't just aesthetic choices, they were crucial for building aqueducts, enabling water to flow over long distances while maintaining a steady gradient. They also played a key role in constructing roads, tunnels, and monumental buildings like bathhouses and basilicas. The brilliance of Roman vaulting was in their ability to distribute weight efficiently, creating structures that could handle heavy loads and last for centuries. And let's not forget the use of concrete. Roman concrete, a mix of volcanic ash, lime, and aggregate, was incredibly durable and made it easier and more reliable to create complex curves and shapes in vault construction. It's important to appreciate the materials. While stone provided the primary structural elements, Roman concrete was the binding force. It wasn't like modern concrete. It was a pozzolanic concrete that used volcanic ash, specifically pozzolana, as a key ingredient. This ash reacted with lime and water, creating a remarkably strong and durable material. Unlike Portland cement concrete, which requires constant moisture, Roman concrete actually became stronger over time. This is because of the formation of calcium aluminum silicate hydrate, which is incredibly stable and resistant to degradation. The Romans also cleverly incorporated aggregate into their concrete. Things like broken pottery shards, crushed brick, and even volcanic rock. This not only reduced the amount of expensive materials needed, but also improved the concrete's workability and strength. The resulting material was highly versatile, allowing them to create complex shapes, build massive structures, and endure the test of time. In bridge construction, concrete was used for the piers, foundations, and even the arches themselves, providing a solid base for the entire structure. Now, let's consider the different designs Roman engineers used for their bridges. While the arch was the fundamental principle, there was considerable variation. One common design was the segmental bridge. Unlike a semicircular arch, a segmental arch is a part of a circle, and it is flatter. This required different engineering considerations, particularly in managing the thrust forces. Segmental bridges were often used for larger spans because they could distribute the load more effectively. However, they also needed more robust foundations to counteract the horizontal thrust. The Romans were skilled at building these foundations, often using a combination of concrete, stone, and timber pilings to create a stable base. Another variation was the tiered bridge, where multiple arches were stacked on top of each other, creating a taller and more imposing structure. These bridges were often used to cross deep valleys or ravines. Beyond the arch itself, the design of the piers was crucial. The piers weren't just vertical supports. They were carefully engineered to withstand the immense forces from the river, the current, debris impact, and the weight of the bridge itself. The Romans often used a pointed or streamlined shape for their piers to reduce resistance to the water flow. They also built cutwaters, projecting stones that further deflected the current. The foundations of the piers were equally vital. They needed to be deep and stable, extending down to bedrock or a firm layer of soil. The Romans frequently used a technique called cofferdam construction, building temporary, watertight enclosures around the pier foundations to work in dry conditions. These cofferdams were typically made of timber and earth, requiring careful construction and maintenance. Finally, the connection between the bridge and the road was essential. Roman roads were well known for their straightness and durability, and this was reflected in the approach to the bridge. The Romans carefully aligned the road with the bridge to ensure a smooth transition for travelers and vehicles. They also paid close attention to the road's gradient, avoiding steep inclines that could make crossing difficult. Typically, the road surface was paved with large stone slabs, providing a firm and even surface. The Romans also included drainage systems to prevent water from pooling on the road and causing damage. This attention to detail ensured that the bridge and road worked together seamlessly, supporting trade, communication, and military movements. Let's now examine a remarkable example of Roman bridge engineering: the Puente Romano in Córdoba, Spain. Built around the 1st century AD, this bridge has stood for nearly 2 millennia, a testament to the skill and ingenuity of Roman engineers. Spanning the Guadalquivir River, the Puente Romano is a magnificent structure composed of 16 arches. Its construction incorporates a combination of stone and concrete, utilizing the principles we've discussed. The piers are carefully designed to withstand the force of the river, and the arches are gracefully curved, distributing the load efficiently. The bridge's foundations are deeply embedded in the riverbed, providing a stable base. The bridge has undergone various repairs and modifications over the centuries, but much of the original Roman structure remains intact. The stonework is remarkably well preserved, revealing the meticulous craftsmanship of Roman builders. The bridge's arches are segmental, providing a wider span and requiring a more robust foundation. The piers are pointed, reducing resistance against water flow. The bridge has survived numerous floods and earthquakes, a testament to its solid construction and engineering principles. The Puente Romano wasn't just a functional structure, it was also a symbol of Roman power and prestige, showcasing their ability to conquer and control the landscape. Today, the Puente Romano is a UNESCO World Heritage Site that attracts visitors from around the world. It continues to serve as a crucial transportation link, connecting both sides of Córdoba, carrying pedestrians across the Guadalquivir River, just as it has for nearly 2 millennia. But more than that, it stands as a remarkable reminder of Roman ingenuity, engineering prowess, and lasting legacy. The bridge's survival through centuries of floods, wars, and natural deterioration speaks to the sophistication of Roman construction techniques. The Romans understood the importance of deep foundations, using cofferdam technology to build underwater and anchoring massive stone piers directly into the riverbed. They also employed lime mortar that actually strengthened over time when exposed to water, a chemical process we're only now fully understanding. The Roman public baths weren't just places to get clean, they were marvels of engineering, and central to this was their heating system. Unlike our modern radiators or forced air systems, the Romans relied on a technique called a hypocaust, from the Greek hypo meaning under and kaustos meaning burnt. Imagine an elaborate raised floor supported by numerous pillars. These pillars or pile stacks created a void beneath the floor. This void was the core of the heating system. Furnaces, typically fueled by wood or coal, heated air, which was then channeled through the space under the floor, circulating around the pile stacks. The floor itself, often made of tiles or mosaics, radiated heat upward, warming the bathers. It's a remarkably efficient system for its time, relying on convection and radiation to distribute warmth evenly. The size of the furnace and the complexity of the air channeling depended on the size of the bath complex and the number of rooms needing to be heated. This wasn't just a simple system, it was sophisticated, requiring skilled engineers and careful construction to ensure even heating and prevent fires. But the hypocaust wasn't just about heated floors. The Romans cleverly expanded the heating system to warm the walls as well. They embedded a network of hollow terracotta tiles called tubuli within the walls. These tiles acted like flues, carrying hot air from the furnace up through the walls and radiating heat into the rooms. This was especially important in the caldarium, the hot room, and the tepidarium, the warm room, ensuring consistent and comfortable temperatures. The tubuli weren't randomly placed. They were carefully integrated into the wall's construction, often sandwiched between layers of brick or concrete. The spacing and arrangement of the tubuli were essential for even heat distribution and preventing cracks in the walls. It was a testament to Roman ingenuity that they could create such a sophisticated heating system using relatively simple materials and techniques. However, maintaining this system was labor-intensive, requiring constant monitoring of the furnace and regular cleaning of the flues and tubuli. The effectiveness of the hypocaust system depended heavily on careful insulation and the overall design of the bathhouse. The floors and walls were often covered with layers of concrete and mosaics, which helped to retain heat. The vaulted ceilings, a common feature in Roman architecture, also played a role in reducing heat loss. The placement of the furnace was crucial. It needed to be close enough to the bath chambers to provide adequate heat, but far enough away to prevent smoke and fumes from entering the bathing areas. The Romans were also skilled at using different materials to control temperature. For example, they might use marble in areas where they wanted to keep things cool and brick or concrete in areas where they aimed to retain heat. The entire bathhouse was designed as a cohesive system, with every element working together to create a comfortable and luxurious experience for the bathers. It wasn't just about heating the water and air, it was about creating a microclimate within the building, a sanctuary from the cold and damp outside. Of course, a bathhouse needs water, and the Romans were masters of water management. They built extensive aqueduct systems to bring fresh water from distant sources, often springs or lakes, directly into cities. These aqueducts weren't just simple channels, they were marvels of engineering that used gravity and precise gradients to move water over long distances. Typically, they combined underground tunnels, above-ground channels, and arches to navigate the landscape. The water wasn't just delivered to the city, it was carefully regulated. Distribution tanks and lead pipes. Although we now understand the health risks of lead, ensured that water reached the bathhouses with adequate pressure and flow. This steady supply was crucial for maintaining the pools and providing clean water for bathing. The quality of the water was also a concern, and the Romans often included settling tanks and filtration systems to remove impurities before the water reached the bathhouses. But having water is only half the battle. You also need to get rid of the wastewater. The Romans were equally skilled at drainage and sanitation. The Cloaca Maxima, literally greatest sewer in Rome, stands as a testament to their expertise. This massive underground channel collected wastewater from public baths, fountains, and private homes, carrying it away from the city and discharging it into the Tiber River. The Cloaca Maxima wasn't just a single channel. It was a complex network of tunnels and passageways carefully engineered to maintain a steady flow and prevent blockages. The Romans understood the importance of sanitation and the connection between clean water and public health. Their drainage systems were not only functional, but also aesthetically pleasing, often incorporating decorative features and vaulted ceilings. Within the bathhouses themselves, sophisticated drainage systems were used to keep the pools clean and hygienic. Pools were regularly drained and refilled, and intricate channels were built to remove dirty water and debris. Settling tanks helped remove sediment, and filtration systems were employed to eliminate impurities. The Romans also recognized the importance of water circulation and aeration, using jets and fountains to keep the water fresh and oxygenated. These systems were not only practical, but also visually appealing, often featuring decorative elements and mosaics. The combination of efficient water supply and effective drainage ensured that Roman bathhouses were not only luxurious, but also healthy and hygienic places to bathe. The Roman baths weren't just places to get clean, they were essential social and civic centers. They provided spaces where people from all walks of life, senators, merchants, soldiers, and slaves, could come together and interact. These baths were used to conduct business, exchange news, and build relationships. Often, they were equipped with libraries, lecture halls, and exercise yards, offering opportunities for intellectual and physical activities. They also hosted entertainment such as music, poetry readings, and theatrical performances. The atmosphere was lively and friendly, with people chatting, laughing, and relaxing. The baths served as a small-scale reflection of Roman society, showcasing its values, customs, and traditions. Politically, the baths served as important gathering places. Senators and other officials often conducted business and negotiated deals within the bathhouse walls. Discussions and debates on current events were common, and the baths acted as a forum for public opinion. The atmosphere was often charged with political intrigue, and rumors and gossip spread quickly. The baths also served as a platform for political rallies and demonstrations. Essentially, they were a place where citizens could engage with their government and exercise their rights. For families, the baths were a place to enjoy quality time together, offering a welcome break from daily demands. They served as spots to relax, refresh, and connect across generations. Families often visited the baths as part of a cherished routine, enjoying the heated pools, exercising in the palestra, and socializing with neighbors and friends. Parents would teach their children to swim in the shallow pools, while grandparents might sit in the warm caldarium sharing stories and wisdom with the younger family members. The baths provided a safe, inviting environment for children, and were often equipped with play areas, ball courts, and other recreational facilities designed specifically for young Romans. Children could run and play while parents watched closely, learning important social skills and Roman customs along the way. The baths were also a popular spot for celebrating special occasions like birthdays, coming-of-age ceremonies, and even wedding festivities, where families gathered in a relaxed, joyful setting. Essentially, the baths were a core part of Roman family life, offering not just physical cleanliness, but also emotional connection, social learning for children, and a communal space where families of all social classes could come together and share in the spirit of Roman community. Let's examine Roman amphitheatres and their foundations, their structural design that gives them lasting strength. Roman engineers didn't just build upward, they cleverly distributed weight to create stable structures. The key to this was the arch. Unlike a simple lintel, which is a horizontal beam spanning a space, the arch directs the load downward and outward, along its curve into supporting piers, or what we call opus caementicium. This Roman concrete wasn't exactly like our modern concrete. It was a mixture of lime, volcanic ash known as pozzolana, and aggregate, like rubble and broken brick. The pozzolana was vital. It allowed the concrete to set even underwater, which was extremely useful during construction, especially when building near water sources. This concrete wasn't used as the entire visible structure, but rather formed the core of many walls and vaults, which were faced with more attractive materials such as travertine or marble. The amphitheatre's walls weren't solid. They were built using a system of barrel vaults, essentially a series of arches extending in a single direction, and groin vaults, formed by the intersection of two barrel vaults at right angles. This created a strong yet relatively lightweight structure, reducing stress on the foundation. Now consider how these vaults were organized within the amphitheatre itself. The seating area, or cavea, wasn't built on a single continuous foundation. Instead, it was supported by a complex network of radial walls and barrel vaults emanating from the central arena. These radial walls acted like spokes of a wheel, distributing the weight of the seating tiers outward. This clever design meant that the amphitheatre could be built on relatively unstable ground. The arena floor itself wasn't a solid slab. Beneath it lay a labyrinth of corridors, rooms, and mechanisms known as the hypogeum. This was essentially the backstage area housing the animals, gladiators, and equipment used in the spectacles. The hypogeum also contained a system of trapdoors and lifts, allowing for dramatic entrances and exits onto the arena floor. The structural integrity of the entire system relied on the precise placement and interlocking of each element. Every arch, every vault, every wall had to be perfectly aligned to ensure that the weight was distributed evenly. Roman engineers achieved this through meticulous planning, precise measurements, and the use of sophisticated tools like the cherabates, a leveling instrument, and the groma, a surveying instrument. It's also crucial to understand the properties of Roman concrete itself. The volcanic ash or pozzolana wasn't just filler, it chemically reacted with the lime to form a cementitious compound that was extremely durable and weather-resistant. Unlike modern Portland cement, which depends on a single chemical reaction, Roman concrete continued to harden over time, effectively becoming stronger with age. This explains why many Roman structures have lasted for over 2,000 years. The Romans also recognized the importance of choosing the right aggregate. They used various materials, including broken brick rubble and ceramic tiles, carefully selecting the size and shape of the aggregate to maximize the strength and density of the concrete. This meticulous attention to detail, combined with the unique chemical properties of pozzolana, resulted in a building material far superior to anything available at that time, and arguably even today. the enduring legacy of Roman concrete is a testament to their ingenuity and their profound understanding of materials science. Now, let's consider how these enormous structures accommodated such large crowds. The seating arrangement within a Roman amphitheatre was far from random. It was carefully organized to reflect the social hierarchy of Roman society. The cavea was divided into distinct sections, each designated for a specific social class. The podium, a wide, elevated platform at the base of the seating area, was reserved for senators, magistrates, and other high-ranking officials. Above the podium were the seats for knights or equites. These were typically made of marble and located closer to the arena. Higher up were the seats for ordinary Roman citizens, divided into sections based on wealth and status. The highest and often furthest seats were reserved for women and the lower classes. This social segregation wasn't just about status, it also served a practical purpose. It helped maintain order and prevent overcrowding. The key to managing such large crowds was a clever system of passageways known as vomitoria, a vivid name referencing how a large crowd could seemingly burst out from the structure. These were arched passageways that led from the outside of the amphitheatre directly to the seating tiers. They were designed to allow spectators to enter and exit quickly and efficiently. The name, while visually striking, accurately describes their function, allowing a massive vomit of people into and out of the arena. Each vomitorium was carefully positioned to serve a specific section of the seating area, minimizing congestion and preventing bottlenecks. The number and placement of these passageways were crucial to the overall functionality of the amphitheatre. They demonstrated the Romans' understanding of crowd dynamics and their ability to design spaces capable of accommodating large numbers of people. Access to the different seating tiers wasn't just about the vomitoria. A network of staircases and corridors also played a crucial role. These staircases were carefully designed to allow spectators to reach their seats quickly and safely. They were often wide and gently sloping, making them accessible to people of all ages and abilities. The Romans also understood the importance of providing adequate lighting. Torches and oil lamps were strategically placed along the staircases and corridors, ensuring that spectators could navigate the amphitheatre even at night. The design of these access routes wasn't merely functional, it was also aesthetically pleasing. The Romans often decorated the staircases and corridors with sculptures, mosaics, and other works of art, creating a visually stimulating environment for spectators. Let's now turn to the logistical challenge of staging these spectacles. The arena floor itself wasn't just a flat surface. It was covered in a layer of sand, or harena, the very origin of the word arena. This sand served several purposes. It absorbed the blood of gladiators and animals, preventing the arena from becoming slippery. It also provided a softer landing for fighters. Beneath the arena floor, as we discussed, lay the hypogeum, a complex network of tunnels, chambers, and cages. This was the staging area for the spectacles. Animals were housed in cages, gladiators prepared for battle, and props and scenery were stored. A sophisticated system of lifts and trapdoors allowed for dramatic entrances and exits onto the arena floor. This subterranean world was a hive of activity, bustling with slaves, trainers, and technicians. The organization of these spectacles was a massive undertaking. Events were carefully planned and choreographed, often lasting several hours. A team of officials oversaw the proceedings, ensuring that the rules were followed and that the spectacle ran smoothly. Gladiators were trained professionals, often slaves or prisoners of war. They underwent rigorous training, learning to fight with various weapons and to endure pain. Animals also played a significant role in the spectacles. Lions, tigers, bears, and other exotic creatures were often pitted against gladiators or against each other. These events were incredibly popular, attracting huge crowds from all walks of life. They served as a form of entertainment, but also as a display of Roman power and wealth. The logistics didn't end with the spectacle itself. Cleanup was a massive task. The arena floor had to be cleared of debris, blood, and animal carcasses. The sand had to be raked and replenished. The hypogeum had to be cleaned and restocked. This was a labor-intensive process that required a large workforce. The Romans were masters of logistics, able to manage these complex operations with remarkable efficiency. Their ability to stage these spectacles was a testament to their organizational skills and engineering prowess. These arenas weren't just venues for entertainment, they were symbols of Roman power, wealth, and ingenuity. We've discussed Roman concrete's remarkable strength, and now let's see how they applied it to coastal defenses. Breakwaters weren't just walls thrown up against the sea. They were carefully engineered structures designed to dissipate wave energy and protect harbors. The Romans understood that direct confrontation with the sea rarely works. Instead, they aimed to redirect and absorb the forces of nature. Early breakwaters were often built using a technique called opus caementicium, which involved pouring concrete into wooden forms built underwater. These forms were frequently filled with stone rubble, creating a composite structure. The key wasn't just the concrete itself, but the strategic placement of heavier stones at the base to resist uplift and scouring. The Romans didn't just build at the coast, they became skilled at building with the coast, incorporating existing rock formations when possible. This not only reduced construction time, but also improved the structure's natural resilience. We'll discuss various types shortly, but remember, the principle remains consistent: energy dissipation through mass and strategic design. Moles, which are raised embankments extending from the shore, formed another important type of protective structure. Unlike breakwaters, which stand alone, moles often enclosed harbors, creating sheltered basins. Building a mole was a significant project, requiring a stable foundation in potentially shifting seabed conditions. The Romans often used a technique called ramming, which involved compacting layers of stone and concrete with heavy pilings driven into the seabed. This helped prevent subsidence and ensured long-term stability. Moles weren't always straight. They sometimes curved to follow the natural contours of the coastline, further improving their ability to deflect waves. They often included internal structures, like retaining walls to prevent erosion from within. Additionally, the Romans would sometimes strategically place smaller secondary moles to break up wave patterns before they reached the main harbour entrance. This layered approach showed a sophisticated understanding of wave dynamics. Think of it like a series of obstacles gradually weakening the force of the incoming waves. Seawalls designed to protect settlements and infrastructure directly along the coast represent a more localized defensive measure. While breakwaters and moles address broader harbour protection, seawalls focus on preventing erosion and flooding of specific areas. These structures were often built using opus reticulatum or opus incertum, variations of concrete construction with irregularly shaped stones. The main point with seawalls wasn't necessarily their height, but a broad, stable base designed to absorb the impact of waves and storm surges. They often featured a sloping face or glacis to deflect wave energy upward and away from the protected area. Roman engineers understood the importance of drainage, incorporating weep holes and channels to prevent water from accumulating behind the wall. These drainage systems helped relieve hydrostatic pressure, further increasing the wall's stability. They also used materials to create natural barriers, reinforcing the base of the wall with layers of gravel and compacted sand to reduce erosion. It was a very effective yet understated coastal defense measure. Constructing a Roman harbour was a logistical marvel demanding meticulous planning and skillful execution. It wasn't simply about building walls, it was about creating a sheltered basin capable of accommodating many ships. The first step involved a detailed survey of the coastline to identify suitable locations and assess the prevailing wave patterns. Then came the construction of caissons, watertight, box-like structures that were floated into position and sunk onto the seabed to form the foundations of piers and jetties. These caissons were often built from wood reinforced with concrete and filled with rubble. The Romans developed sophisticated techniques for underwater concrete placement, using wooden forms and diving bells to ensure accurate and efficient construction. Remember the pozzolana we discussed? That was crucial for creating concrete that could set underwater. This was especially challenging, as maintaining structural integrity underwater required concrete that was both strong and durable. The construction of piers and jetties required a network of scaffolding and cranes to lift and position the massive stone blocks and concrete elements. Roman engineers were masters of leverage and mechanical advantage, employing a variety of pulleys, winches, and capstans to accomplish this feat. They also developed a system of temporary wooden cofferdams, watertight enclosures, to create dry working spaces within the harbour basin. These cofferdams allowed them to excavate the seabed, level the foundations, and construct the piers and jetties without constant interference from the tide. The careful alignment of these structures was crucial for creating a safe and efficient harbour. Roman engineers used a variety of surveying instruments, including the groma and dioptra, to ensure precise measurements and accurate construction. We spoke of the levelness of Roman roads. The same principle applied here. Once the piers and jetties were finished, the harbour basin needed to be dredged to provide enough depth for ships to navigate. Roman engineers used various dredging methods, including hand-operated scoops and levers, as well as more advanced mechanical devices powered by water wheels. The dredged material was then utilised to create artificial islands or strengthen the harbour walls. To improve the harbour's protection, Roman engineers often constructed a series of breakwaters outside the main entrance, designed to dissipate wave energy before it reached the inner basin. These breakwaters were usually built from rubble and concrete and carefully placed to deflect incoming waves. They also took into account silting and sediment buildup, designing structures to promote flow and prevent blockage. It was a comprehensive approach to harbour design, considering both immediate construction needs and long-term maintenance. Roman harbours weren't just engineering achievements. They were essential centres of commerce and military strength. The Romans knew that controlling the seas was crucial for maintaining their empire. Harbours like Ostia, Portus, and Alexandria served as gateways for trade, linking Rome to distant parts of the Mediterranean. These ports enabled the import of vital goods such as grain, wine, oil, and luxury items, as well as the export of Roman manufactured products and agricultural produce. The large volume of trade passing through these harbours required efficient infrastructure, including warehouses, docks, and customs facilities. Roman engineers designed these structures to handle high cargo volumes and reduce congestion. The harbours also played a key role in supporting the Roman navy, offering safe anchorages for warships and spaces for repairs and maintenance. It's easy to see them as vital gears in a very large machine. Roman naval bases were strategically placed throughout the Mediterranean, creating a support network for the fleet. These bases were usually fortified with strong walls, towers, and gates to defend against attacks. They also housed various facilities for repairing and maintaining warships, such as dry docks, workshops, and warehouses. The naval bases served as staging areas for military operations, allowing the Romans to project their power across the Mediterranean. They also played a vital role in maintaining maritime security by protecting trade routes from pirates and other threats. The ports essentially formed the backbone of Roman military strength. They enabled the rapid deployment of troops and supplies, helping the Romans respond quickly to emergencies and maintain control over their vast empire. The prosperity of Roman harbour cities was directly linked to the efficiency of their harbours. A well-designed and maintained harbour could attract merchants and traders, generating wealth and stimulating economic growth. Harbour cities also served as centres of administration and culture, attracting skilled workers and fostering innovation. The construction of harbours and port facilities required significant investment, but the economic benefits far outweighed the costs. The Roman government recognised the importance of harbours and actively promoted their development through public works projects and favourable trade policies. The enduring legacy of Roman harbours can still be seen today in the remains of ancient port cities and the continued importance of maritime trade in the Mediterranean region. They represent not just engineering prowess, but a masterful understanding of logistics, economics, and the power of connection. It truly shows what an impact a civilization can have when they build for the future. While concrete was revolutionary, the Romans certainly didn't abandon other building materials. Brick, stone, and especially marble continued to play vital roles in construction, often alongside concrete. Brick, or lateres as the Romans called it, wasn't the neatly uniform product we often see today. Roman bricks varied significantly in size and quality. They were typically made from clay, moulded, and then sun-dried or kiln-fired. While not as strong as concrete, brick was relatively inexpensive and easy to produce, making it ideal for walls, vaults, and facing structures. It was commonly used in areas where concrete wasn't practical or aesthetically desired. Think of the interior facing of concrete walls. Brick provided a smoother, more refined surface. They also used brick for creating arches and vaults because it was lighter to work with than stone, allowing for greater spans. Different brick types existed, like signatum, which had impressed markings indicating the legion or manufacturer, providing a level of quality control and demonstrating that the Romans were very organized in manufacturing. Stone, particularly travertine, tufa, and limestone, was favored for monumental structures, temples, and public buildings. Travertine, quarried extensively near Tivoli, was prized for its durability and aesthetic appeal. The Romans developed sophisticated quarrying techniques using tools like wedges, picks, and levers to extract large blocks of stone. The process was incredibly labor-intensive, relying heavily on skilled workers and brute force. These stone blocks were then transported to construction sites using ramps, rollers, and sometimes even waterways. The cost and weight of stones limited their use to prestige projects and foundations. The Pantheon, for example, utilizes massive travertine columns and a concrete dome, demonstrating a skillful combination of materials. The exterior facing of many Roman structures, even those built with concrete cores, was often clad in stone, providing a more visually impressive and durable facade. The Romans knew how to work with natural variations in stone, utilizing different colors and patterns to create decorative effects. Marble, especially the white marble from Carrara, was the ultimate luxury material. reserved for the most important structures and decorative elements. Marble signified wealth, power, and refinement. Roman architects and sculptors skillfully exploited the beauty of marble by carving intricate details and creating stunning sculptures, mosaics, and architectural features. Marble was used for column shafts, capitals, floors, and wall veneers, elevating the aesthetic quality of buildings. The cost of quarrying, transporting, and carving marble was substantial, meaning it was mainly used in imperial palaces, temples dedicated to major deities, and the homes of the very wealthy. Consider the extensive use of marble in the Forum of Trajan, a testament to the empire's wealth and artistic prowess. Unlike concrete or brick, marble was often imported from distant quarries like Greece and North Africa, adding to its expense and prestige. The Romans weren't just using materials, they were making statements about their power and cultural sophistication. While concrete, brick, and stone formed the primary structural elements of many Roman buildings, timber played a crucial and often underestimated role, especially in roof construction. Roman carpentry was highly skilled, and timber framing techniques were refined over centuries. Timber was readily available throughout the empire, making it a practical and cost-effective material. Roofs were typically built using a framework of beams, rafters, and purlins, creating a sloped surface for drainage. The type of wood used varied depending on availability and cost, but pine, fir, and oak were common choices. The Romans developed sophisticated joinery techniques, using mortise and tenon joints, dovetail joints, and wooden pegs to create strong and durable connections. These joints, often combined with metal bracing, ensured the roof could withstand heavy loads and adverse weather conditions. Roman roofs were not simply framed with timber, they were covered with a variety of materials. The most common roofing material was terracotta tiles known as tegulae and imbrex. Tegulae were flat tiles used to cover the main surface of the roof, while imbrex were curved tiles used to create a watertight overlap. These tiles were carefully arranged to form a sloping surface that effectively shed water. The Romans also used other roofing materials such as slate, marble slabs for prestigious buildings, and even lead sheets. The weight of the roofing material was an important consideration, as the timber framework needed to be strong enough to support it. The Romans often incorporated gutters and downspouts to channel rainwater away from the building, preventing water damage. Proper roof construction was essential for protecting the interior from the elements and ensuring the structure's longevity. Roman architecture often incorporated unique roof designs, especially in atria and basilicas. The atria, the central courtyards of Roman homes, often featured an open roof called a compluvium, which allowed rainwater to collect in a basin below called an impluvium. This design provided both light and ventilation, while also collecting water for household use. Basilicas, large public buildings used for administrative and legal purposes, often had timber-framed roofs with a shallow pitch. These roofs were usually covered with terracotta tiles or lead sheets. The Romans also experimented with various roof shapes like gable roofs, hip roofs, and mansard roofs, depending on the building's function and aesthetic needs. The use of timber framing and innovative roof designs helped the Romans create spacious, well-lit, and functional buildings that met the needs of a growing empire. Beyond the structural materials, Romans invested heavily in decorative elements and finishes. Frescoes painted directly onto wet plaster were a prominent form of wall decoration. These vibrant paintings often depicted mythological scenes, landscapes, portraits, and geometric patterns. Roman artists were skilled at creating realistic and expressive figures, as well as complex, colourful compositions. The quality of the frescoes varied depending on the wealth and status of the owner, but even modest homes often featured some form of wall decoration. The use of colour was an important aspect of Roman interior design, with bright and bold colours being favoured for their aesthetic appeal. Different pigments were derived from natural sources such as minerals, plants, and insects. Mosaics were another popular form of interior decoration. These detailed designs were made by arranging small pieces of stone, glass, or ceramic, known as tesserae, onto a prepared surface. Mosaics were often used to decorate floors, walls, and ceilings, creating stunning visual effects. Roman mosaic artists were skilled at making realistic and expressive images, as well as complex and geometric patterns. The subjects of mosaics varied depending on the wealth and status of the owner, but common themes included mythological scenes, portraits, landscapes, and everyday life. The process of creating mosaics was time-consuming and labor-intensive, requiring skilled artisans and high-quality materials. Stucco was a versatile material used for both structural and decorative purposes. It was a type of plaster made from lime, sand, and water, and could be applied to walls, ceilings, and columns to create smooth surfaces or intricate relief carvings. Roman craftsmen were skilled at creating elaborate stucco decorations depicting mythological scenes, floral patterns, and geometric designs. Stucco was often used to imitate more expensive materials like marble and could be painted in a variety of colours. It was a popular choice for both public and private buildings, adding elegance and sophistication to interior spaces. The use of stucco allowed the Romans to create visually stunning and durable decorative elements that continue to inspire awe today. The Roman construction boom wasn't just about manpower. It was deeply influenced by a sophisticated organization of skilled professionals. At the very top were the architecti, who weren't simply designers in our modern sense. They were comprehensive project managers responsible for conceiving the entire project from initial planning and budgeting to overseeing construction and ensuring its completion. Think of them as a mix of architect, civil engineer, and construction foreman all in one. These were often men of high social standing, sometimes even freedmen with exceptional skills. They didn't necessarily lay bricks themselves, but their vision and planning were crucial. They were also skilled in mathematics, geometry, and materials science, essential for ensuring structural integrity. Their designs weren't impulsive. They were carefully calculated to withstand the test of time, a testament to their expertise and the Roman emphasis on practicality. Below the architecti were the agrimensors, or surveyors. These individuals were responsible for accurately measuring land, establishing boundaries, and laying out the foundations for structures. They used sophisticated tools for their time, like the groma, a device similar to a quadrant used to establish right angles and straight lines. Their work was absolutely vital. Even a slight miscalculation could lead to structural instability or the collapse of an entire building. They weren't just measuring land, they were translating abstract plans into tangible reality. They also kept detailed records, maps, measurements, and material inventories, essential for project management and accountability. It's worth remembering that Roman engineering wasn't just about brute force. It was about precision and meticulous planning, and the agrimensors were key to achieving that. Then came various specialist craftsmen. The lapidarii, stonemasons, cementarii, concrete specialists, tignarii, carpenters, and aquarii, plumbers. These were not just laborers, they were highly skilled artisans. who had refined their craft over years of apprenticeship. Each group had a specific role and worked together in a surprisingly organized manner. For example, the carmentarii were responsible for mixing and applying concrete, a Roman innovation we'll discuss in detail later. The tignarii built wooden scaffolding, formwork, and roofing structures. The aquarii designed and installed water pipes and drainage systems. This division of labor promoted efficiency and specialization, ultimately enhancing the scale and quality of Roman construction. It's impossible to discuss Roman labor without acknowledging the widespread role of slavery. While skilled craftsmen were essential, a significant portion of the workforce consisted of enslaved individuals. These weren't just unskilled laborers. Many were former soldiers, captured artisans, or educated people forced into servitude. They performed a wide range of tasks, from quarrying stone and transporting materials to mixing concrete and building structures. The conditions were often brutal, and the work was physically demanding. Although some enslaved individuals possessed valuable skills, they were rarely recognized or rewarded for their contributions. It's important to remember that Roman engineering achievements were built on the backs of countless enslaved people who endured great hardship. However, the workforce wasn't solely made up of enslaved people. Free laborers also played an important role, especially in more specialized trades. These workers were often skilled artisans who earned wages and generally had better working conditions and more independence than their enslaved counterparts. In many cases, free laborers and enslaved individuals worked side by side on the same projects. This created a complicated social dynamic with tension and inequality built into the system. While enslaved people provided most of the manual labor, free laborers often supervised the work, offering expertise and ensuring quality. The interaction between these two groups was key to the success of Roman engineering projects. Regardless of their status, whether free or enslaved, all laborers required significant training and skill. Roman engineering wasn't about simply throwing bodies at a problem, it was about applying knowledge and expertise. Apprenticeships were common, with young workers learning from experienced craftsmen over many years. These apprenticeships weren't just about learning technical skills, they also instilled a sense of pride and craftsmanship. Skilled laborers were valued for their ability to produce high-quality work, and they often enjoyed a degree of social standing within their communities. The Roman emphasis on practicality and efficiency demanded a workforce that was both numerous and skilled, achieved through a combination of slavery, free labor, and rigorous training. As we've discussed throughout this course, Roman engineering was remarkable, but even the strongest systems are vulnerable to decline. It wasn't a sudden collapse, but a gradual erosion, and the reasons were complex. One major factor was, unsurprisingly, economic strain. Maintaining such a vast infrastructure, the roads, aqueducts, baths, and buildings, required enormous resources. As the empire stretched thin, diverting funds to constant military campaigns and a growing bureaucracy, maintenance budgets were often cut. This wasn't just a matter of being frugal. The enormous size of the empire made logistics a nightmare. Getting materials and skilled labor to distant provinces became more difficult and costly. Think of the vast distances involved and the reliance on sometimes unreliable trade routes. Political instability also played a major role. Frequent power struggles, civil wars, and the division of the empire into eastern and western halves caused constant disruptions. This resulted in inconsistent policies, corruption, and a collapse in governance. Skilled engineers and laborers, once valued and protected, found themselves caught in the crossfire or simply sought more stable jobs elsewhere. This brain drain further weakened the empire's ability to maintain its infrastructure. Additionally, reliance on slave labor, while initially cost-effective, proved unsustainable. Slaves lacked the motivation and specialized skills needed for complex repairs and innovations. As the supply of slaves decreased due to fewer conquests, the quality of workmanship declined. Finally, there were environmental factors. While Roman concrete was remarkably durable, as we've discussed, it wasn't impervious to the elements. Constant exposure to rain, frost, and seismic activity gradually took its toll. The quality of materials also varied, and the use of pozzolanic ash, while generally beneficial, sometimes resulted in unpredictable reactions over time. In some regions, the water supply used in concrete mixes was contaminated with harmful chemicals, accelerating the deterioration process. All these factors combined created a slow but inexorable decline, gradually weakening the foundations of Roman engineering achievements. Despite the decline, a surprising amount of Roman engineering knowledge was preserved. Unlike some civilizations where knowledge was passed down orally, the Romans were prolific writers. Treatises on architecture, engineering, and construction techniques were documented by authors like Vitruvius, whose De Architectura remains a cornerstone of architectural history. However, much of this knowledge wasn't fully understood or appreciated for centuries after the fall of the Western Roman Empire. During the early Middle Ages, a period often referred to as the Dark Ages, many Roman texts were lost, neglected, or simply misinterpreted. Libraries fell into disrepair, and the skills of Roman engineers were gradually forgotten. The emphasis shifted from practical engineering to religious construction, and innovation stagnated. Fortunately, the rediscovery of Roman ruins during the Renaissance sparked renewed interest in classical engineering. Architects and engineers began studying Roman structures firsthand, marveling at their ingenuity and durability. The rediscovery of Vitruvius's De Architectura in the 15th century was particularly significant, providing a wealth of information on Roman building techniques. This led to a revival of classical architectural styles and a renewed emphasis on mathematical proportions and structural integrity. However, even with the rediscovery of these texts, some Roman knowledge remained lost. For example, the precise composition of Roman concrete, particularly the use of specific pozzolanic materials, was not fully understood until relatively recently. Modern researchers have spent years analyzing Roman concrete samples, attempting to recreate its remarkable properties. This modern research has shown that Roman concrete was not only extremely durable, but also surprisingly eco-friendly. Using volcanic ash as a binder greatly lowered the carbon footprint of concrete production, making it a more sustainable material than modern Portland cement concrete. This finding has sparked renewed interest in adopting Roman concrete techniques to develop more sustainable building materials. The legacy of Roman engineering thus extends well beyond the impressive structures they created. It continues to influence and inspire modern engineering practices and provides valuable lessons on sustainability and durability. For centuries, the longevity of Roman concrete has fascinated engineers and historians alike. It's not just that structures have lasted, but how they have endured that is so remarkable. Modern concrete, although initially strong, degrades over time and requires constant repairs and replacements. Roman concrete, however, actually improves with age. This is not due to some lost arcane knowledge, but rather a combination of materials and, surprisingly, the deliberate inclusion of weaknesses. They weren't aiming for a perfectly homogeneous, flawless material. Instead, they embraced a unique mix of volcanic ash, lime, and aggregate, with pozzolana being the key ingredient. This pozzolana reacts with seawater to create a binding calcium aluminum silicate hydrate, basically a strengthening mineral that fills cracks and makes the concrete more resilient over time. Think of it as a self-healing mechanism built into the very foundation. The Romans weren't shy about using materials that might seem imperfect. They deliberately incorporated quicklime, which causes micro cracks to form. This might seem counterintuitive, doesn't it? But these cracks, far from weakening the structure, were essential to the self-healing process. Seawater flowing through these cracks dissolved the volcanic ash and quicklime, creating the mentioned calcium aluminum silicate hydrate. It's this ongoing cycle of cracking and repairing that gives Roman concrete its remarkable durability. Modern concrete, by comparison, aims for impermeability to block water from entering, but this also prevents natural healing processes and can lead to pressure buildup from trapped water, causing spalling and structural failure. The Roman method was to accept water ingress and turn it to their advantage for structural benefit. The composition of the concrete itself was also strategic. They used a wider range of aggregate sizes, everything from large stones to finely ground volcanic ash. This dense packing reduced porosity and increased the overall strength of the material. Moreover, the use of pozzolana wasn't merely about its chemical reactivity, it also reduced the amount of water needed in the concrete mix. Less water meant less shrinkage and fewer cracks forming during the curing process. It's a holistic design philosophy, embracing imperfections, leveraging natural processes, and prioritizing long-term resilience over short-term perfection. Understanding these principles is crucial as we seek to create more sustainable and durable concrete for the future. Modern concrete production has a significant environmental impact, mainly because of the production of cement, a key ingredient. Cement manufacturing releases large amounts of carbon dioxide into the atmosphere, contributing to climate change. However, a wave of innovative approaches is emerging to address this challenge. One promising area is the development of supplementary cementitious materials, substances that can partially replace cement in concrete mixes. These include fly ash, a byproduct of coal-fired power plants, slag, a byproduct of steel production, and silica fume, a byproduct of silicon production. By utilizing these waste materials, we can reduce the demand for cement and lower the carbon footprint of concrete. Beyond supplementary cementitious materials, researchers are exploring entirely new concrete alternatives. Bioconcrete, for example, incorporates bacteria that produce limestone, effectively self-healing cracks as they form. Hempcrete uses hemp fibers as aggregate, creating a lightweight, breathable material with excellent insulation properties. Mycelium composites harness the power of fungal networks to bind materials together, offering a sustainable and biodegradable alternative. Recycled aggregate, crushed concrete, glass or plastic, is increasingly used to reduce the demand for virgin materials. These innovative approaches represent a shift toward a more circular economy, minimizing waste and maximizing resource efficiency. The challenge isn't simply developing sustainable materials, it's integrating them into existing infrastructure and construction practices. This requires collaboration among engineers, architects, policymakers, and material scientists. We need to incentivize the use of sustainable concrete through government regulations and financial incentives. We also need to invest in research and development to further improve these technologies and make them more cost competitive. The future of concrete isn't about abandoning the material altogether. It's about reimagining it as a sustainable, resilient, and environmentally responsible building material. It's a complex task, but one vital to building a more sustainable future. The lessons from Roman concrete's durability, self-healing qualities, and adaptability are more relevant than ever in the face of climate change. As sea levels rise and extreme weather events become more frequent, our infrastructure must be designed to withstand these challenges. Engineering for resilience isn't just about building stronger structures, it's about creating systems that can adapt and recover from disruptions. This requires a holistic approach that considers the entire life cycle of a structure, from design and construction to maintenance and decommissioning. It also involves embracing innovative materials and construction techniques. Nature-based solutions that harness the power of ecosystems to provide infrastructure services are becoming more important. Mangrove forests, for example, act as natural buffers against storm surges and erosion. Coral reefs help protect coastlines from wave action. Restoring and conserving these ecosystems not only improves resilience, but also offers valuable ecological benefits. Combining these solutions with traditional engineering approaches can lead to more sustainable and effective infrastructure systems. This shift involves changing our mindset from seeing nature as something to be controlled to viewing it as a vital partner in building a more resilient future. Looking ahead, the future of engineering for resilience lies in embracing smart technologies and data-driven decision-making. Sensors, drones, and artificial intelligence can be used to monitor infrastructure performance, detect potential problems, and optimize maintenance schedules. Real-time data analysis can help us adapt to changing conditions and respond to disruptions more effectively. This requires a collaborative approach that brings together engineers, data scientists, and policymakers. By combining the wisdom of the past with the innovations of the present, we can build a more resilient and sustainable future for all. It's not just about building structures that last, it's about creating systems that thrive.